double integral, right? Remember that was still double integral. Double integral xy, and we switched to polar coordinates r theta or theta r, something like that. But it's still double integral. Your d is in xy plane. Now we're switching to triple integrals, right? Okay? Remember the difference between double integral and triple integral? Double integral main motivation was volume, right? What was the main motivational problem for triple integrals? Density, and if you integrate it triple, you get total mass, right? So that's the main motivation. So why are we doing this again? To do change a variable, just like xy coordinate change to polar coordinate, right? And you've been looking at examples of this standard parameterization. One is called cylindrical coordinate system, and the other one is a spherical coordinate system. Rather than using x, y, z, use r, theta, and phi, right? You look at the position in a different way. All right, so in general, it goes like this. Do you have a question, sir? Rho should be the rho. For spherical, but cylindrical, we still use r. Yeah. In general, if you are looking at x and y and z coordinates, and you parameterize it with the three different variables, s and t and u, right? Okay, it's just like rho, theta, and phi. That's the one example of this thing. Spherical coordinate system. Make sense? In general, if you have that, we compute the Jacobian variety like this. Not Jacobian variety, just Jacobian x, y, z, and stu. You look at it's written in the matrix is written in column way. It's x, y, z, right? All differentiated with respect to same variable s. X, y, z, all differentiated with the second variable. X, y, z, and third variable. You see the kind of the pattern and how it's differentiated? Which is consistent with a 2 by 2 Jacobian. Right? You write down xy vertically, column vector, and partial differentiation with the same variable. However you memorize it correctly. This is the Jacobian matrix, right? So what does this mean? Here's a parameter space, STU, right? And this is a real space. Yes, sir. Did you have a question? Yes, I apologize. Wasn't. It has to be rho and XYZ. Is that your point? Okay. Sorry about that. Okay, it has to be there. And what else? So here's a parameter space. This is a real space, right? But we look at the parameter space like r, theta, and phi. So you don't really see this type of space, or just like before, you can pretend this is different lenses, stuff like that. So in STU, you have a nice, very nice, perfect cube in there with delta S there and delta T there, delta U there, right? But to this guy, this looks like some jello shape inside fastly accelerating train. You know, parallelepiped or jello, you're swinging around like unstable. This picture makes sense? It's a horrible picture. But think about, slanted jello shape. So, what about the volume of this one? And is correctly approximated by the Jacobian. You calculate it times the volume of this one. Delta S, delta T, delta U. The volume is approximate. If it is linear transformation, and then it's going to be parallelepiped, the volume is exactly equal to Jacobian times delta S times delta T times delta U. But if it is not linear, such as spherical coordinates, it is approximate, and they're claiming is good enough to make this integral equal. Okay? So this volume multiplied by its density is actually the mass of the sample. So you integrate it like this. Alright? Same principle, one more variable. Make sense? Alright, let me give you some. Alright, how was this parallelepiped problem? Were you able to generalize the parallelogram thing we did for double integral? So this is just a random picture. parallelepiped. I'm sketching it here. And the other side, there was this. So there's, you know, 3 vectors. Okay, that's a parallelepiped. If you have any points interior in here, and you move parallel to one of your choice of a vector, it could be this one, it could be that one, move parallel, and until you hit this point on the other face as you move parallel. Then you can generate that vector using the bottom 2 vectors, using parallelogram law. And then if you add that vector here to that vector with this another parallelogram law, you can reach that. So any inside points, there is a scalar multiple of this bottom 2 vector and another scalar multiple of this, the other remaining vector. You can reach that vector by adding those 3 vectors. And in this picture, I think it's intuitively it's clear that those scalar multiples are all less than 1 or 1 because it's inside the parallelogram or this top part in there. So it makes sense? Yeah. So we have these 3 vectors, and by multiplying these 3 scalars being less than or equal to 1 or greater than 0, you reach everywhere. So if you expand this one, you have parametrization of x and y and z. I think I wrote here like this, and so if you multiply s and multiply t and multiply u to these components and combine them together, and you arrive at here, x being s minus u, y being t minus u, and so on. So this is xyz with respect to partial with respect to s there, right? This one here, xyz partial with respect to t, correct? And this one here, partial with respect to u. And in general, if this is not linear like this, you will have some s and t in there. So it changes, but if not, that means, you know, it's always parallelogram, perfect parallelogram, not curved side or anything like that. So computing this integral over the triple integral over this parallelogram is the same as computing different solid v, which is coming from STU space, right? And because they vary freely like this, and that's a perfect boundary when you enter iterated integral for that part, is all 0, 1, 0, 1, 0, 1, right? Yeah. And then you have to multiply the Jacobian, which is the determinant of this one and 2. And it happened that this integral, when you enter iterated integral, happened to be the 1, so it coincides with its 2. Right? In general, you have s and t inside the Jacobian factor, and but this was a simpler case. But if you think about just calculating this one, usual case, projection, figure out which and above and which planes are there, like six planes are here, right? Since there are 6 sides, and that would be a horrible calculation. You can even imagine and how ugly that calculation can be, right? This idea of this Jacobian allows you to calculate this in a lot better way. All right, that's the point of this exercise. See the how neat this idea is, right? The Jacobian factor. All right. Any question you might have about this example? The next one was a standard parameterization. So rho is fixed, and I want you to think about these points in it here. I'm going around like this, and this is actually x coordinates sticking out. Same orientation. If I move around like this, what is varying? Rho is fixed, right? So rho is not varying. It's about theta or phi. If I'm moving around like this, is rho is varying? I mean, phi is varying or theta is varying? Theta is varying, right? If it's rotating around z-axis, what is varying? Theta is varying. But rho is fixed, right? This rho is fixed. So do you think it's roughly what's your estimate of this rho value here if it is phi is fixed? Pi over 4? Does that make sense? This is where phi equals 0, right? The vertical phi equals 0, and you open, wide, and that's where, sticking out, that's the angle to the center. So let me use z and y and z axis. This is kind of same orientation you get out of the first octant of XYZ space, right? So this is the section of the sphere. We're looking at that point right there, for example, on that point, or on that point here, over there. So that's phi angle. That's how we understand phi, right? From the North Pole to how much is wide. Okay? So phi usually varies from 0 to where? All the way up to, not 2 pi, all the way up to here. So this is like as wide as it gets, right? All the way down there. You don't go beyond that because theta will take care of the rest of the part. Rotating by theta, you'll reach the other side. So you don't go more than pi. You start from 0, go all the way down to the South Pole, and don't go beyond it. So anything that we describe, spherical coordinate system, varies only from 0 to pi. However, theta varies from where to where? All around 0 to 2 pi. Not for this one. In general, this is you're trapped in this number in here. Rho can vary anywhere, right? From 0 to positive infinity. So rho varies from 0 to infinity. You can make it as large as you want. By varying these three variables in that way, we reach every point in the space. Correct? Yes. I understand. Alright, so if I vary vertically like this, from here to there, what varies? Theta is fixed, right? Only phi varies here. Phi varies. Okay? So, if you feel comfortable with the rho being fixed, and if they're describing a certain region, I want you to go into a fixed region like this and think about, what about this region? How are we going to describe this region in here? Think about what is a phi value. Phi value is here fixed. Phi value here is a fixed. You get that 2 phi value, right? And you look about this one. This is a theta value fixed, and that's a theta value fixed. So this is the typical rectangular, the spherical coordinate region where phi and theta and rho does not depend on each other. They freely vary within certain smaller range of this. You start from this one. Then you have to make this rho slightly bigger, right? To getting shape something like this. I hope I've... so this picture kind of makes sense. This is where rho is constant. They choose the wrong letter here. Rho. And this is another outside. That's what rho is fixed. And this side here, as you can see, if you think about that sphere picture, this is where theta is fixed. And this is where phi is fixed. Think about the cut. Does that make sense? Yeah. So here's exercise I wanted to have. The final bit. The Google thing didn't sync. Right, so let me just write that down. So I want you to go and sketch this region. That's why. Rho being in between 1 and 2, and theta being pi over 2 to pi. That's problem number 1. Separate question. or just one exercise. Rho being varying 1 to 2, and theta varying pi over 2 to pi. However, there's no condition on phi. Phi can be anything. If phi can be anything, what does that mean? Varying from 0 to pi. That's what it means, right? 0 to pi. So you can put, if there's no condition on phi, you can put phi being 0 to pi in there to make it more specific. And after you sketch it, if possible, I want you to come up with some sort of fruit term. This resembles some sort of fruit. I don't know. However, you will be able to relate this shape with a where does the theta at 0 start? Theta 0 starts from positive x-axis. That's where theta 0 is. And toward to positive y-axis. That's the direction of theta rotation. It's like cantaloupe cut in half and core removed. That's what I call, you cut cantaloupe in half, right? And you remove that seed from inside, and then it looks more like that, right? Before you cut it further. So this is where theta equal 0, right? It starts from theta equal pi over 2. This is where pi over 2 is, right? Oh, I was wrong. The pi, this should be 3 pi over 2 to get that. So another quarter cut in there to the pi. This, what I had in mind, I wrote down this wrong thing. So let me go ahead and fix that. We don't have that side, right? Only the quarter of that side. So let me draw this picture again. We have some sort of, what got trickier. No, this is pi over 2, and only go pi over 2 more, so you only stops at this side. You don't go all the way around, right? Right, yeah. Yeah, like that. Hope that makes sense. Yeah? So it's a quarter cut of the cantaloupe. And then that's a pi over 2, and the other side, and yes. Right. Right, so phi works like this. If you have z over there and y there, think about the sphere. This is where rho is 1 and 2, right? In between 1 and 2. This is where phi equals 0. This is where phi equals pi over 2. This is where phi equals pi. Right. I would more look at yz because that's the plane we're facing. But you can use xz too. But definitely I will keep the z in there because the angle phi is relative to z-axis. So if I look at this one in here, that's the angle phi. Right. So here, This is where theta equals pi over 2, correct? If it's in the YZ plane, this is pi over 2. So rho varies freely in here. Right, freely in here 1 and 2, and phi varies from freely 0 to pi. So this is where phi equals 0. This line in here is where phi equals pi over 4. This is pi over 2. This is 3 pi over 4. And this is where phi equals pi. Right, because you go over and you will end up at, if your theta move around, and that corresponds to the same thing, yeah. So that it can describe things like this. Other than that, it just continue go like you're saying, covering all that. So phi has to stop at pi. So that's usually what they mean by that. So this one is rotated between pi over 2 to pi. That's a good way to look at it. But phi is not rotation. Phi is a bit more tricky. But if you have condition about rho and theta, that rho and phi, the theta part is really the rotation. That is correct. So if you look at theta pi over 2, and there's no other limits that involves rho and anything, then it's simply rotating this one up to pi over 2 around z-axis. So I hope you see this picture resembles that. Good? Okay. Number 2, I think I had it at 1 and 2. Oh, not 1 and 2. Just rho being 0 to 2, and phi being 0 to pi over 4. This will be a bit challenging. But think about some line segment. Maybe you're going to start with in YZ plane. Begin in YZ plane. Maybe that's going to help. In YZ plane, ignore theta, where YZ plane where theta equals pi over 2, right? Theta equals pi over 2. Then sketch the region where rho varies from 0 to 2, and phi varies from 0 to pi over 2. Then if there's no condition in theta, what are you going to do? Just rotate it around z-axis 0 to 2 pi, and that's it. But for theta, you are allowed to rotate around all the way 0 to 2 pi. But phi only from 0 to pi. That's a good point. Yes. Yes, that's right. I hope, did you make sense out of the YZ plane thing? So if you just look at the YZ plane where theta equals pi over 2, then rho is varying between 0 and 2, so the 0 is here and 2 is there, right? Or the distance. But there's no particular orientation for phi, whether you're going to this side or that side. It's just relative to z. So there's no, again, there's no orientation to that side or that side. It's only relative to z. So we should include this and that. But it's also symmetric in taking care of out 0 equals pi over 2 pi as well. Yes, exactly. Yeah. But if I put constraint on theta equals pi over 2, just that plane, the pi over 2 does not include this side of the plane, right? So if I just say if this is really theta pi over 2, I should get rid of that part. If I constrain to this theta equals pi over 2 is not the entire plane, only the half of the plane, right? Yes.
And the top domed portion
right.
Because of the unconstrained theta.
This part here?
Yeah.
Right. Theta means rotating around it here. You have full shape all around because there's no constraint on theta. Right. That's right. Is that good? Final challenge is that all three of them is kicking in here. Let's see if we can do that. Number 3. Rho is in between 1 and 2. Theta is in between pi over 2 to 3 pi over 2. How about that? I think that change that to pi over 2 to pi, 3 pi over 2 so that I can see. I think it is easier. And rho phi is from 0 to pi over 4. See if we can sketch this shape. Well, my preference, I would start in a YZ plane and then rotate, begin from pi over 2 to all the way up to 3 pi over 2. Hope this makes sense. Then you have a full cone, but you remove the bottom of the cone where the chocolate part is in the ice cream. The chocolate part is removed, and then cut it right in half. And so, this one here, this one. Some of the things that we practice, I share the video with you, but this is the first one. Pi over 2 to pi, right? from yesterday. That does look like cantaloupe cut it out with the core removed, right? Like I promised. And this one was, what was this one? Anybody remember this one? What was a constraint in there? Is there any constraint in theta? No, all around, right? What is the constraint on phi here? 0 to pi over 4, right? 0 is here, pi over 4 is there. No more. And how about rho? Starting from 0 all the way up to whatever this one is, right? 2 or whatever. So rho varying from 0 to 2, right? And phi varying from 0 to pi over 4. So that was an example. Does that make sense? Yes? Any question? And this one was, this side here is pi over 2, theta being pi over 2, right? All the way across there, the theta being 3 pi over 2. Here's rho is 1, cut it out. This is where rho is 2. How about this side here? That also came from phi being pi over 4 from positive z-axis, right? So that was the third one we practiced yesterday. I also posted a video where I actually rotate this around, so you can watch that to get a better view. But I think this gives you some idea of how it looks like. So that was earlier yesterday's exercise and the three things. Think much about how you parameterize it. So this is a cylindrical coordinates. X and Y coordinates the same as the polar coordinates. Z, they did nothing, right? So Z is useful as well. So with this one, with respect to R and theta and Z in that order, did you find that Jacobian being just simply R, right? That was easy because there are lots of zeros in there, right? Any question about this one? This time, the Jacobian is not constant. It depends on how far you are from the 0, 0, right? Yeah. The second one was the cylindrical coordinates. That how about this one? It took some calculation to do the determinant with a lot of Pythagorean identities in there, right? But eventually got there. To get the negative, the answer was negative rho squared sine phi, right? So what did you do? I used this Lagrange Laplace expansion on the bottom row. This one times, because of the zeros there, right? And then that one. That's what I did. This one gets positive, and that one 0, and that one, you remove the rows and column and calculate and all that. However you did it, whichever rows and column you use, you must arrive in the same answer, negative rho squared. And I was explaining in the study group message that the negative was caused by this weird thing about phi. Phi, when phi equals 0, is go to the top of the positive z coordinate. When phi is pi, z corresponds to negative 1 coordinate, right? So it's kind of little disorientation. So that causes negative. But if you just swap the order or something, this variable in here, so instead of having this column over there, column over here and there, that changes the sign of a determinant, so it puts back in the right orientation. Well, all that matters is magnitude, the volume, and so simply just put absolute value like I did in here, will take care of it, right? As long as it doesn't flip sometimes positive and sometimes negative within your parameterization. That would be terrible. Parameterization would be good, but consistent sign, and that will cause no problem. Alright, so even though it turns out like this, we use positive rho squared and sine phi. The phi varying from 0 to pi, so sine theta phi is always a positive number, right? That's another interesting part. Phi varying from 0 to pi, so sine phi is always a positive number, so we know it remain always negative number, so we definitely have to change to positive sign. Alright, so we memorize it. We don't calculate this every time when you see, right, spherical coordinate. You remember the Jacobian we use is a positive rho square sine phi. Okay? And the cylindrical coordinate system, when do we use cylindrical coordinates and when do we use spherical coordinate? My idea is usually if you project it onto xy plane, if that looks like a good polar region, right? That's usually the cylindrical coordinate, right? But also consider spherical coordinates. Sometimes, even though your projection is still good for cylindrical coordinate, but sometimes the spherical coordinate is better. Just like entire sphere or shells of a sphere outside, things like that. I think it requires a bit of practice and experience. How about this one? This looks like a good cylindrical coordinate, right? If you project it onto xy plane, that's a typical polar region. And z varies from kind of constant to constant in here. So that's a typical good region for polar coordinates. Not polar coordinates, cylindrical coordinates. Does that make sense? Yeah. And this is cylindrical coordinate with the Jacobian being r. So I want you to memorize this one. If you're using cylindrical coordinate, the z is the same as, z is untouched here. Then the Jacobian is r. Let's remember, what was the Jacobian? I want you to use a triple integral, not calc 2 or double integral method. So how do you compute a volume in terms of triple integral? We set what equal to 1? Density rho equal to 1. So you triple integral integrate which function? Constant 1. Then that's a volume, right? The volume equals the mass if the density is 1. So find the volume of the intersection of ellipsoid. Remember ellipsoid? Egg shape, right? And the cylinder y squared plus z squared equals 1. Why don't we change this y squared z squared equals 1 to x squared to y squared equals plus y equals 1 so that it's easier to project it on down. I think projection might be good. I hope it's not cutting out too much there. I think it's safe to do that. 10 is large enough. So you have to make a decision. Cylindrical coordinates or spherical coordinates, right? It depends on the shape, but there is a cylinder, the word cylinder in there. So if it is bounded by these two things, it's definitely inside the typical cylinder x squared plus y squared equals 1, right? So in my opinion, it's probably the cylindrical method is better. But I want you to first consider these ellipse and think about x-intercept and y-intercept and z-intercept. See how big this ellipse is and see how the cylinder cut out this one. So you have to be able to visualize this one to make a decision that, oh, I do agree that cylindrical coordinate is better than spherical coordinate. So I first try to sketch the picture of this one. The cylinder is natural, nice projection onto xy plane being the circle, right? So I compare this one and how this one cut out in xy plane. So I wrote down the ellipsoid equation and see how this one cut out xy plane where z equals 0. So if you plug in z equals 0, x squared plus 2y squared equals 10. So that's an ellipse with x-intercept root 10, y-intercept root 5. So the circle is definitely sitting inside the ellipsoid, right? So how is it going to cut out? I hope you see that there's an ellipsoid outside like there. It continues in three-dimensional way. But the core x squared plus y squared is just kind of make a hole through the center from the top. So this cylindrical shape with the top and bottom coming from ellipsoid is the region they're talking about, right? So its projection image down there is a circle. So it's good for cylindrical polar coordinates, right? Z have to be just slightly different. Okay? So how is Z varying from, down to top? That's the question, right? So if that's the W, we have this formulation, this W in there, and rho is 1, correct? And dx, dy, dz, that's what we have to calculate. Now we're about to change the variable. Think about how this z value must vary, and xy, you can use the polar coordinates, right? So that's the second part in there. Try to go to iterated integral immediately. Like, I hope you understand. The z is inside first, then r and theta, whatever the order you use. So I use the spaces in there. So I want you to enter iterated integral in terms of cylindrical coordinates. Think about where z has to vary first. And there is density function 1. And what is the Jacobian? R, right? R, so that's it. Yes, sir. Alright, makes to make things easier, I think I'll just formulate it, because if 2 is multiplied this one and that one, you can complete the problem. Otherwise it gets a little bit difficult. So I'm going to just stop in the formulating this one. So in this formulation, what is z here down there? So 10 minus x squared minus 2y squared, right? The plus minus, the bottom one gets minus and top one gets a plus 1, right? So you put on there negative root 10 minus x squared minus 2y squared up there. The positive root 10 minus x squared minus 2y squared. But this x and y must be later replaced with r and theta, right? Whole thing divided by 2 should be correct. Yes, thank you. And that should be 2 in there. 1/2. Thank you. Is that right? All right. Then, how about r and theta? Because your polar region is just a perfect circle, so r varies from where to where? 0 to 1. Theta? 0 to 2 pi. Right? So the projection is a perfect circle that corresponds to this polar region. R equals 0 to 1, theta being 0 to 2 pi. Okay? So when you integrate inside, r is treated as a constant, right? So what is the inside part? 0 to 2 pi out there. 0 to 1. So that's 2 times of this one, right? Because antiderivative of 1 is just a z, so this one minus that. So turns out r times root of 10 minus x squared minus 2y squared, negative 1 half times 2. So it's dr d theta. Yes, sir. Right. This is the ellipsoid, and that's the ellipsoid equation, and that's what I used here. Yeah. You're right. You're right. He has to. That's right. You go inside there. Thank you for the further correction. You're right. So therefore, we have another ugly constant here, and what is that? 2 divided by root 2, right? 2 divided by root 2, which is, if you rationalize, is the same as root 2. Okay. Yeah. So. Okay. And if we had the 2 in front of it, so if I put 2 and 2 there instead of 2 in there, this inside will be simpler, right? So, but because of the 2, it all messed up, so it's harder to integrate. But I'm just going to focus on formulating this one into integral and stop there. So, how's the last bit? The 2 pi in there, and the 0 to 1, square root of 2r, and what we do in there? We change that to 10 minus r squared cosine squared theta, right? Minus 2 times r squared sine squared theta, correct? And then inside there's a dr d theta. But this is not 1 in here. If these coefficients are the same, then this is going to be simply r squared, right? Negative r squared. Then because r out there, we could do change of variables. But if it's being like that, it's a lot harder integral. I don't even know how to do that at this point. But it was a formulation, and again, the original problem was y squared plus z squared. And in that case, that behaves nicely in there. So if I put 2 in front of x squared, 2 in front of y squared, and no 2 in front of z squared, this would have been easier integral. But let me just stop in here in terms of formulating into cylindrical coordinates. Make sense? So I will change that problem in the homework. So put 2 and 2 in front of that, and in front of z squared 1, and then you can finish this problem as this one cosine squared sine squared becomes 1, and you can use u substitution so that this derivative outside, it does everything works nicely. Yes, sir. This is y squared and z squared. I will use that y squared z squared as a polar coordinates, and x is x equals x, like I suggested. So that's how we should have done that problem. But I just want to stick to xy since that's what I've been doing. So, and then we had to change this problem as well, right? Okay, make sense? Yes. All right. So let's just focus on formulating. Sketch the region and enter cylindrical coordinate system and go to the change of variable like this. This is called elliptic integral. Very hard when the number is different. Yeah. Okay. Any question in terms of formulation? Fair enough? Okay. So number 18 seems like something you have done, so you immediately see this is probably better with which system? Just spherical system, because the region itself is a perfect, spherical bowl, so no need to enter cylindrical system. Spherical bowl will be easy, right? Spherical coordinate change of variable will be easy. So again, so let's just do this together and we'll move on. It's not an exercise, we'll do this one together. So what is our change of variable in this case? X equals, let's get it out. Let's see. It's the same as, think about like this polar coordinate. Polar coordinate is r times cosine theta, right? Y equals r times sine theta. You remember that much, right? Instead of r, we use rho and trigonometry. And z is easy. What was z? Rho times cosine phi, right? If you look at weird z in there, that's what. This is height, right? So here's a z, and here's a phi, right? What is the z coordinate of that one? Is this length. That length is adjacent to phi, right? Adjacent to phi, cosine. So that's how you're going to remember this one, right? Z coordinate is adjacent to phi, rho cosine phi. How about the other one? Whatever the alternative is. Rho sine, right? Rho sine phi and rho sine phi. That is this length here, opposite. That served as the radius of that horizontal cut. If you think about the sphere, that cut in there, that latitude, that cut, this is the radius for that cut there. So, but focus to the simple one in here. The z coordinate is adjacent to phi, so it's simply like that, and r is replaced by this one, right? So that all this thing replaced this one in there, right? So what is this integral? All this x squared plus y squared, z squared, you already know that is, what is this one then? Actually, this is going to be rho squared, right? Let's witness that. X squared plus y squared plus z squared. You see x squared plus y squared, these two things are common. So as you square that, this pulls out as a common factor. This squared plus that squared is what we have for x squared plus y squared. And z squared is rho squared cosine squared phi, right? So that's 1. Then rho squared and rho squared is common. And sine squared plus phi squared, again, is 1. So inside just remaining just rho squared, right? But what do we have to multiply when you change variable? Jacobian. What was the Jacobian of the spherical coordinates? Rho squared sine phi. Then everything becomes spherical coordinate in d rho, d theta, and d phi. Or you can swap around the order because there's no constraint between each other. So rho's inside from between 0 to 1, that indicates that. How about theta? 0 to pi, and be careful with phi. 0 to pi only. That's the convention. If you go over, that overlap with the phi. Do you have a question, Carter? Oh yeah, that's right. Yeah, I forgot that. Thank you. There was this thing forgotten, so you have to put back in now. Thank you. So in that way, this rho squared phi. So that's iterated integral. Good. So that was the example they have in the exercise is pretty simple. The one that I chose earlier, 16, was one of the hardest one, I think, in there. So it's a fairly simple. You don't see quarter cut of a cantaloupe, anything like that in the exercise. But I thought it was a standard thing to cover. Any question about spherical and coordinate? But like I did in the exam 3, I will share the picture with you if this is going to be on the exam. This is how the shape of a, region, three-dimensional figure. All right, good. Right, that's an end of a multiple integral. It has section and application. It has moment of inertia, center of mass, that thing. But that's simply just executing the formula. So I encourage you.